Now let's get into the nitty-gritty of weathering. Weathering comes in two main flavors. First, physical weathering. This is the disintegration of rock without changing its chemical makeup. Think of it like breaking a large cookie into smaller pieces. It's still a cookie, just smaller. Some examples that we're going to discuss are frost wedging, heating and cooling cycles, salt crystallization, and also abrasion. For frost wedging, first you got to be in a cold climate. And what happens is water seeps into cracks in the rocks. And when it freezes into ice, it expands like 9%, acting like a wedge and prying the rock apart. The force is incredible of when water freezes into a solid and it expands. It's able to, as you can see, bust this huge rock apart. For heating and cooling cycles, that's where it warms up, then gets cold, just kind of changing of temperature, not really looking at the added effect of frost wedging or water. What happens there is the rocks will expand when heated, so they get bigger, and contract when cooled, especially on the outer regions of that rock, because that's where most of the temperature change occurs. Over time, this constant stress can cause the outer layers to peel away, kind of like an onion, if you think of it. Now, in some dry climates, salts can crystallize in rock cracks, exerting internal pressure and splitting the rock, kind of similar to frost wedging. Salt air, specifically salt spray, causes this dramatic pitting like you see here on the left. Sea wind splashes seawater onto the rocks, and as that salty brine dries out, the salt crystals grow in the pore spaces and gradually pry the mineral grains apart. This process, called cavernous or honeycomb weathering, affects inland sites where the rock itself contains salts. Uh, Mount Diablo and Las Trampas Ridge in California have great examples of that. That's where this picture comes from. But along the coast, it acts much faster and more pervasively. Now, for some nerdy geologic terms, the hollows are often called tuffoni, and the smaller ones are called alveoli, which is kind of like the sacs in your lungs. It's a similar word. Now on your right, this is an image of a rock formation showing abrasion. Abrasion is the constant wearing away by wind-blown dust, rain, running water, and also physically breaks down the rock surfaces. Many national monuments in the western U.S. feature wind abrasion rock formation. The image here on the right, that's actually a rock formation in central Sahara from wind-blown sediments. Let's start with the fundamental process in chemical weathering called dissolution. This one might be a bit easier to visualize because you have seen it happen in your everyday life. Do you think about what happens when you put a sugar cube, a scoop of sugar in your coffee, or say maybe try to dissolve some salt in water? The water molecules, because of their unique structure, are really good at getting in between the atoms or ions that make up a mineral. They literally pull those individual atoms or charged particles, what we call ions, right off the surface of the mineral. It's like they're gently picking them off one by one and taking them away. The key characteristic of dissolution is that when the mineral breaks down, there's no solid residue left behind. It just seems to disappear into the water. The mineral atoms or ions are now completely dispersed and dissolved within the water, like sugar in, say, your iced tea. They're still there, just not in a solid form you can see or even feel. A classic example would be, say, limestone. This is the chemical formula for limestone. And when it reacts with water, this right here, this arrow again means yields. The calcium breaks off into a calcium ion, a positive one, which makes it a cation, meaning that this thing has lost 2 electrons. And then also you have the other part of the mineral, the carbonate ion. It's an anion because it's negative. It's gained 2 electrons. And then you still have water floating around. So this is the process of dissolving. And to review some other terms, you have your solution, you have what's being dissolved, the solute, and then the dissolver, the water, the solvent. All right, let's dive into the next chemical weathering process, hydrolysis. Don't let the chemical equation down at the bottom intimidate you again. Okay, we're just going to break it down in a way that makes sense. The chemistry part's not something to memorize, but it, kind of goes along with chem and quant, and will play a role later being able to understand the chemistry side of things. So first, let's think about water. Well, it isn't just H2O floating around perfectly intact. Even pure water, to a tiny, tiny extent, can actually split apart or dissociate, which is what we just talked about in the last slide. Water will break down into 2 charged pieces, a hydrogen ion, which we write as H+, and the hydroxide ion, which is OH negative. Think of it like a tiny invisible pair of scissors splitting the water molecule. These little charged pieces are what make hydrolysis happen. Now, here's the magic happens in soil formation. These newly formed hydrogen and hydroxide ions are highly reactive. They don't just float around. They're actively seeking out and chemically combining with minerals and rocks. When they combine, they actually change the mineral's chemical structure. It's not just breaking it into smaller pieces like physical weathering. It's fundamentally changing what that mineral is. So a good way to remember this is, breaking this down. Hydro means water, you know that. Well, lysis means to cut. Okay, so it's water cutting. basically. Now, let's look at a common example here. We have a mineral called orthoclase. We don't know exactly what that is yet because we haven't got to the rock cycle and talking to rocks, but that's the chemical formula for it. And it's a type of feldspar. You'll recognize that word once we get to rocks, the rock lab. And when it undergoes hydrolysis, it doesn't just dissolve, okay, when freeing those ions. Instead, it chemically transforms into a new mineral, often a type of clay. Okay, this is different than this. Will have different properties and is usually smaller and softer. And it also releases some other ions into the soil solution, such as hydroxide and sodium. This process is crucial because it creates the clay particles that are so important for soil texture. It's important for holding water and also nutrient retention. Okay, so besides splitting things apart, it's important to remember dissociation will break things apart, and sometimes those are usable mineral nutrients for plants. But also you have hydrolysis, which dissociates things, breaks it apart, and rearranges things into a whole new softer mineral. Hydration is another form of chemical weathering. So think of this as minerals literally like getting thirsty and absorbing water. Okay? Unlike dissolution, where the mineral breaks apart and disappears, or hydrolysis, where water chemically cuts the mineral, in hydration, the entire mineral actually absorbs water molecules right into its internal crystal structure, reacts with the mineral, becomes chemically bonded to it. And it's like a sponge. The sponge doesn't dissolve, but it definitely changes when it soaks up water, doesn't it? So when these water molecules get absorbed into the mineral structure, they take up space. This causes that mineral to expand in volume. Think about what happens when you pour water into a dry, cracked mud puddle, right? The mud expands and becomes softer. This expansion puts stress on the mineral, creating internal pressures and literally weakening its structure. It becomes less dense and even more fragile. And this weakening is the key. A mineral that has undergone hydration is now much more vulnerable to other types of weather. It's like softening up a tough cookie before you try to break it. It becomes easier for physical forces like freeze thaw or for other chemical reactions to further break it down. So if we look at this chemical equation here, you have hematite, which is a mineral pictured here, and it's going to react with water. Now, the way that it's written here is that it's dissociated, but still kind of together, right? It's still a water molecule, two H's and an O. Well, it yields into a new mineral once that water becomes attached chemically to that structure and becomes a whole new mineral, limonite, which is this one. Once you see it in the lab, it's very brittle, breaks apart easy, it's less dense, and it breaks down even quicker. Well, we'll talk about that part next. All right, let's tackle oxidation and reduction, often called redox reactions. Don't let the term scare you. Think of it like a chemical seesaw where electrons are being passed back and forth. This is super important to soils, especially how colorful they are and how nutrients behave. Now, here let's look at oxidation. This is where minerals will oxidize, meaning it loses an electron. Imagine an atom literally giving up one or more of its electrons. A simple way to remember this is oil rig. Oil will be oxidation is loss. This often happens when minerals are exposed to oxygen, like in well-drained soils or when certain microbes are active. Now, the other part of oil rig is talking about reduction. This is where substances gain electrons. Okay? So if one mineral loses an electron, another mineral or element has to gain it. The rig is reduction is gain. This typically occurs with very little or no oxygen is available, like waterlogged soils or deep underground. Now, this is common in elements like iron and magnesium. And these elements often have multiple forms or oxidation states. And iron is one that we will be most familiar with, and understanding some of the common names with it is important. You have the reduced form of iron. It's a 2+ cation. That's called ferrous. And once it becomes oxidized, where it loses an electron, it's called ferric. That's when it is a +3 cation. Okay, and so you look down here at the bottom. This is the chemical equation for hematite. This is spectacular hematite. You'll see this in the lab. We found this in Arizona. And this is the chemical formula for it. And as it oxidizes, the iron loses electrons, then it turns into ferrous oxide, which is this rusty look. And these redox reactions cause parent material to form softer minerals. That's why it's very important. Now, this is going to be very important in future parts of this class and next semester, is recognizing the oxidation state of iron, commonly viewed by the soil's color, because it will be an important characteristic of hydric soils, which is a part of wetland delineation. But just to introduce that, let's look at how redox affects soils here, okay? So it causes dramatic color changes. When iron is oxidized, it gives a soil that red, orange, or reddish brown color, okay, like you see on this side. You know, you could think of bright red soils in Georgia. Okay, those are oxidized soil, lots of oxygen available. On the other hand, when iron is reduced, which is usually the case when it's waterlogged and oxygen can't get to it, the iron then causes a soil to be very gray, even bluish to greenish hues. These colors tell us a lot about the drainage and the oxygen levels in the soil. So you can just by looking at the soil color, you will be able to infer a lot about its chemical environment. This is what we'll be looking for when we are looking to delineate wetlands. We want these glade soils that have gray, bluish, even greenish tinge, or at least modeling. And these are our typical soils. To wrap up this section on weathering, let's touch on the effect that plants have. Plants just aren't passive residents now. They are active agents in crumbling rock and creating soil. One way is root wedging. As roots grow, they can exert an incredible pressure, up to like 150 pounds per square inch, directly into rock cracks, physically prying them apart, as seen in this image of a conifer splitting a boulder as it grew. Another way is by secreting acid. Moss and even tiny lichens, those crusty growths you see on rocks, produce mild acids that slowly dissolve the rock surface. Plant roots themselves also release mild acids that further that chemical weathering process. And of course, when plants die, their dry matter is added to the developing mixture of mineral and particles and organic matter, enriching that soil. So now let's take a little break and let's review and answer a few questions.